are these studies?
Maybe just the sound is good.
Okay.
Maybe a bit more.
I mean, I agree. I think
You should speak a bit so that he.
I
keep the volume down until the introduction is done, and then I'll raise it.
Okay, you can control it. I mean, that's nothing I. Okay. Good.
Okay, so let's start. So now we'll have. Let's start. Now we'll have a talk by Tim Maudlin, who will talk about fine-tune, unfaithful, unnatural abuse of terminology in causal modeling. So the floor is yours.
Okay, thanks. Good. So I think I can get through this in pretty decent time. Let me do the prologue, which contains two theses. One is that language is the medium by which we communicate, formulate clear propositions, and propose compelling and convincing arguments. Thesis 2, language is the medium by which we engage in miscommunication, engender confusion, and get misled by bad arguments. And obviously, they're both true. And it means we have to be awfully careful if we want to understand each other and understand what's going on in exactly what various pieces of terminology mean. So here's the tentative plan. This has been adapted to what's happened. So let me just go over the plan. So I'm just going to begin going over a list of terminology that's problematic. Okay, you ought to be careful about it. I'm not saying don't ever use it, but sure, think a bit about what it means when you use it and try and think a bit about what it means when somebody else uses it, because they might mean something different. Some not so problematic terminology. Usually when you drill down on any of these things far enough, you run into some issues. But at least at first pass, this seems okay. Then I want to do this just because it was clear not everybody has seen this argument, and it's just beautiful. If you want to go to sleep and then wake up for this part and then go back to sleep. Okay, because this is really cool. If you've never seen this, this is just tremendously cool. This GHZ argument. And then I want to talk about how certain phenomena are explained causally, the causal structure, the explanation, in a particular way of understanding quantum theory. And you get a very clean account. It's a surprising one. And it's one that I think some people are not familiar with. And so it's useful. And then finally, the title, this is what I thought all I would be talking about, is some particular terminology that comes up in the causal modeling literature and that has been brought over in people worrying about quantum theory, the idea being, okay, we have these issues trying to understand quantum theory. Maybe if I go to this other literature and apply it, see how it applies, I can make some progress, right? But I think actually we've made anti-progress by doing that for reasons I'll give you. Okay. So here's some problematic terminology. Some of this has been used in this meeting. Sometimes people say something is classical as opposed to quantum. There are classical causes and quantum causes, or classical probabilities and quantum probabilities. There's classical logic and quantum logic. Okay. Here's a word which you might not think is problematic, but I'll explain why it is. The word theory. Here's another one, hidden variables, which, well, I don't need to do this now. I'm going to come to these things. This is just to warn you. The terms contextual and non-contextual, which actually have been used, I'll show you. And the terms realist or realism, which sometimes come up in discussions. And this is very general. If you're in this area, you better get clear about this stuff. Let me just talk about this one. I'll talk about this one in the most detail. I give you a theory. And then I say, okay, you tell me, right? I'm going to give you the theory. Now you tell me whether it's a classical theory or a quantum theory, right? What do you do? What do you look at? Okay, we've had an explicit suggestion that was made. We've had actually a couple of them that were made early on the first day. One is that, well, ask yourself, can the states in this theory, the physical states, be cloned, right? Or broadcast, duplicated, whatever you like. And on the quantum side, there's an actual formal argument here. The no cloning theorem, which runs from the unitarity of the Hamiltonian evolution to saying there just can't be a unitary evolution that takes as an input some state and gives as an output two copies of that same state. All right, that's clean if all you've got is unitary evolution. But on the classical side, if you say, but gee, in any classical theory, you can clone states, you can copy states. I give you a state. In principle, you ought to be able to copy that state. Oh, yeah? I've never seen a theorem of that. I don't even know how you'd begin to prove such a theorem, right? So classically, I hand you a box of gas, okay? And it's got 10 to the 23rd different particles in some position and velocity distribution. And you're telling me, well, in principle, there's some, I don't know what machine I can build that'll build me copies of that in exactly that same state. I don't know how you do it. I don't know how you go about trying to prove such a theorem. I don't even know what it means. Right? So the idea that somehow, well, classically everything is clonable, not in any practical way, certainly. No theorem of the sort, you wouldn't even know where to begin. So I'd be worried about this. If clonability is the issue, it's not clear that classical theory is classical. There's another suggestion made. Classical states are in some way controllable. Same issue here, right? Because of course, if everything were in principle perfectly controllable, then they'd be clonable, right? Then, gee, of course, in principle, and I specify to you a state of a gas, right, in a box with 10 to the 23rd particles, and I tell you exactly where I want each particle and exactly what velocity I want it, and I say, here, go build me that. Okay, if you can do that, then you can clone it because you can just build it again. But who says you can do that? By what principle could I even begin to prove a theorem that you can do it? Because now you need a whole theory of what you can do. Where does that come from?
This is the starting point. You said that you start from a theory, so it's a theoretical problem.
I'm raising questions here. I don't want to get caught on this stuff. Okay. But I'm just saying, if you want to claim you can prove this, stop a minute and think. Okay, I'm going to talk about a theory in a second, so then I'll come back. I can give you a theory, but still not answer all the questions you would need to prove a theorem. So here's a data point. This is just sociology. I'm going to talk a lot about this theory called Bohmian Mechanics, the pilot wave theory. And just, it's true that many people who don't like the theory run down people who like the theory by saying, oh, you're all conservatives and you just can't get with the quantum program and you're stuck with classical ways of thinking. And this is a classical theory, right? So some people will say Bohmian mechanics is a classical theory. But sure, it gives all the same predictions as quantum mechanics. So you might think it's a quantum theory. What do you mean? Now, personally, I think I just don't think there's any payoff to this, right? I mean, I could sit here, you could make different proposals, what makes something classical, but who cares? Some piece of terminology, right? Deal with the theories in front of you. Well, deal with the theories. What's a theory? Now, here I've got a big complaint. I've made this forever. Some of you will have heard this. People talk about theories. They talk about classical theories and quantum theories. They talk in particular about a thing, quantum theory. I use this term in a very specific way. For me, to have a physical theory means you've provided me within epsilon. Okay, there might be some fuzziness, but pretty well you've provided me with two things. You've specified an ontology and a dynamics. What does that mean? I specify the ontology by telling you what the theory postulates to exist, to be real, to be in the world. Okay, as opposed to being epistemic or some function of somebody's beliefs or whatever. And the dynamics, once you've given me the ontology, the dynamics then specifies how the ontology behaves. I usually do that by giving you some dynamical equations. Okay, to me, that's what a theory is. And by that standard, if you open a usual textbook that has the title quantum theory, it doesn't give you a theory. Okay? Because it's just not clear what's actually being physically postulated. You use a wave function. Does it represent something physically real? You use some collapse postulates. Is that something that's really going on in the world? Is that merely epistemic? Are you just updating on information? Standard textbook won't tell you. Just won't. Now, so I can give you all that and give you a proper theory and still not have answered questions that were relevant to controllability, because that requires then talking about, well, who's doing the controlling? I mean, this was all, in a way, this was Maxwell's point with his demon. He said, look, we big fat human beings with big stubby fingers can only do such and such. And we can't convert thermal energy in a box at equilibrium into useful mechanical energy, but this quick-fingered little guy could do it. So to make the distinction of what can and can't be done, that's one that connects up to thermodynamics, you actually have to talk about human beings, what they can do. And that can change, right? That's not part of the theory as I stated it, right? Because that's part of a hypothesis about human beings, God knows. I wouldn't want to have to do that. Okay, the term hidden variables comes up a lot. John Bell says in a nice place that the things called hidden variables in quantum theory, he says it's a piece of historical silliness that term is used. He was 100% right. You might think it's just the same thing as latent variables in causal modeling. It really isn't. So that's just warning for people in the causal modeling literature. When you see hidden variables in the quantum context, don't think, oh, that's just latent variables that I'm used to. In particular, I'm going to talk about Bohmian mechanics. And there are pieces of the ontology which are actual particle positions, which are called hidden variables. Okay. But man, they are not hidden. If they were hidden in the normal sense of hidden, you couldn't see anything. In fact, what you basically see when you open your eyes and look around at the world is the positions of things. And in this theory, it's the positions of things that happen to be made up of particles. And the positions and shapes and so on of large objects made up of small particles is a function of the positions of those small particles. I mean, as Bell said, what's really hidden in Bohmian mechanics is the quantum state. That's kind of hidden. Not that you can't get at it entirely, but it's not easy to get at. So just be careful when you see that. Again, my suggestion, avoid the term altogether. We don't need it. This distinction, contextual and non-contextual, that comes up in discussions of quantum theory too. And I think this is also kind of terrible terminology, very misleading. Why? Really what it means is that a theory is contextual means that the outcome of an experiment can depend on how the experiment is done. Thank you. Okay, yes. Now, it's a little more specific than that. There's a way in which certain experimental setups are associated with Hermitian operators in quantum theory, and it can turn out that physically different setups get associated with the same Hermitian operator. And in a contextual theory, what's really going on in that experiment may depend upon which of those setups you're using. Okay, even though they're associated with the same Hermitian operator. But ultimately, you're just saying the way an experiment works depends on how it's actually done, the physical way it's implemented. Oh, okay. That is, people who think, oh, there's something weird about this theory, it's contextual. No, it'd be incredible if theories were not contextual in the sense of you want to understand an experiment, take into account the physics of the experimental situation. The terms realist and realism come up a lot. I've saved the worst for last. It comes up terribly in this, people say this stuff. Bell's theorem refutes local realism. But they say, gosh, I love locality. You will prize locality out of my cold, dead fingers. So, okay, I'll give up the realism part and keep the locality part. I like to say this is the position. Nothing actually exists, but thank God it's local. This is just, this makes no sense, whatever. Technically, there is a good meaning to the term scientific realism that comes up in the epistemological literature. In philosophy, it means a very specific thing. I don't even have to go into it because it has to do with epistemology, not with metaphysics, not with ontology, not with physics. It has to do with what certain evidence entitles you to reasonably believe. But that's not a physical question. And the term realism shouldn't be showing up in these discussions at all. Good. Okay, so that's some bad terminology to avoid. Here's some good, pretty good terminology, local. So in a relativistic setting, and for all practical purposes in a non-relativistic setting, you can assign a sharp meaning given to the modifier local. So this one's good. In particular, locally, causal theory is one where what? All of the causes of an event sit in or on the past light cone of the event. And in a relativistic theory, that's all well defined. So if you're going to have causal arrows in a locally causal theory, they got to run. They can't, as it were, go faster than light. Now, you don't have light cones in a classical theory, but for all intents and purposes, you can talk about things going faster than light, even in a classical setting. All right, so this is pretty good. And you've got causal locality, and you can talk about signal locality, which is similar, but where you say a theory is signal local if you've got what would normally be considered a setup that you can use to transmit arbitrarily chosen messages, that the transmitter, in order for the thing to work, the transmitter has to lie again in or on the past light cone of the receiver, where there are transmission events where you press the button and reception events where somebody sees a blip on a screen. So a local, local signaling, that's pretty well defined. So that's good. Now, what's the basic idea for locality? Why is that good? Well, why should you think a theory ought to be locally causal? Because you think causes have to precede their effects, right? And when you're sending messages, the person pushing the button, that event has to precede the reception of the signal. And that's why in the standard causal modeling literature, you insist on an acyclic graph, right? That's what the A is all about. You've got an acyclic graph because things can't go around in causal circles at the level of specific individual causation, because that would require going around in temporal circles. And, absent weird stuff about time travel and blah, 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 that can't happen. Right? That's why you want DAGs. Now, of course, if you're talking about causation at a more generic level, you could have feedback loops that have circles in them. But you think, yeah, but that's only because I'm agglomerating things at a generic level. I'm coarse graining in a certain way. If I get down to the specific individual events, you never get circles. Good. Now, in relativity, if you just start with that idea that causes have to precede their events, in relativity, when events are space-like separated, that is, when they lie outside each other's light cones, they have no definite causal order, temporal order. So if you demand that causes precede their events, you can't have causal connections between space-like separated events because they don't have a temporal order, right? So this puts a nice constraint on the kinds of causal models you're allowed in a locally causal theory. Yes? Now, here, notice the idea here that you have a restriction on causal arrows that's given by the relativistic constraint. This is of absolutely zero interest to people doing economics and people doing epidemiology. You're never going to have to worry about that, right? You are never, ever, ever dealing with separate events that are at space-like separation, okay? All the events you deal with, giving somebody a shot, whether they get sick and blah, 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 right? You change their education and then what happens to their income. All of that has a perfectly clear temporal order, even taking relativity into account. So this idea of this sense of a locally causal theory will really be of no interest. Now, I suppose one could have other reasons for thinking theoretically there ought not to be causal relations between some nodes in a graph, right? And you could sort of impose that and then get similar results, but they won't be the ones that came up for Bell, right? They won't be the ones we're going to be talking about. Those come up because of relativistic considerations. Okay, now we get to Bell's theorem. So what does Bell actually prove? He shows that if you do some experiments at space-like separation, which means I don't have a definite temporal order in relativity, there are certain just observable results from those experiments that cannot be replicated, predicted, or explained by any locally causal physics. Right? That's the content of the theorem. Now we could, again, there's always epsilonics and there's a statistical independence assumption that goes in, but that's what the theorem really tells us. And then we can conclude something from it because we actually do these experiments and we find that they violate the inequality that he proves, and we draw the right conclusion. Actual real physical physics in the actual real physical world is not locally causal, which is really quite a surprise. I mean, you really ought to be surprised at that. Now, the exact definition of Bell locality, we could go into some epicycles about, but you should just go and read. There's a late paper called La Nouvelle Cuisine by Bell, where he gives his most kind of explicit account of exactly what he means by locality. And there's some stuff about Markov consideration, so on, but not really relevant. And in this talk, really signaling doesn't come up, right? If you prove that the theory can't be locally causal, you might then worry, okay, I've got non-local causation. Can I then use it for creating non-local or superluminal signaling? Okay, and that's an interesting question, but it's not anything that Bell's worried about, right? Bell isn't talking about signaling, he's talking about causation. Okay, so then we get this DAG that's always used for the CHSH stuff. And you see what's going on, that the state preparation of a pair of particles lies to the past of some experiment Bob does. Bob himself is way over here making some experimental decisions. Alice is way over here making some experimental decisions. And this are space-like separated from this and this. So if it's a causally local theory, I can't put any arrows going from here to here or there to there. Yeah, so I'm restricted to a graph like that. And then you ask a question, all right, what kind of statistics can this structure recover? And that's the usual Bell theorem. The usual Bell theorem in the sense, the one he actually proved, and notice this is a bipartite experiment where I'm dealing with a pair of particles in a particular quantum state. Now, what apparently may not be so familiar is that much later, Greenburger, Horne, and Zeilinger were fiddling around with this stuff, and they came up with this really beautiful example, GHZ example, which is different from Bell's. It's more complicated in a way because it involves not a pair of labs, but a triple. So now we've got Bob, Alice, Bob, and Charlie, but their labs are arbitrarily separated so that the decisions they make about what to do in their labs and the outcomes of their experiments that they record in their labs all happen mutually at space-like separation from the others. Okay, so we can say in a locally causal theory, again, we can't have arrows running across this thing. What's nice about this example is that the relevant predictions are all deterministic, right? They're not in the Bell case, the relevant predictions are in part, they're partly deterministic and they're partly statistical. So to test it, you've got to run the experiment many times, or anyway, to get anything you would think of as an actual empirical outcome that could that checks this, you've got to run the experiment many times because you're checking statistics against statistical predictions. But in this case, they're not. They're all surefire 100% all the time, every run predictions. That's what's so beautiful about this. It tells you that the probability part isn't really playing a role. When Merman first, I read about this stuff from David Merman, and he said Merman had worried a lot about Bell's theorem. He said, I always thought somehow it was important to the theorem that it be fundamentally statistical. And he said, and then I read this, I was wrong, right? Okay. So that's why I want to go through this. Now you can wake up. Now the important part. Okay, so here's schematically the situation. I have a source that's going to create a triple of particles in a certain well-defined quantum state. It's going to send the 3 particles out in 3 different directions. I've got Alice, Bob, and Charlie that sit in their labs, and I can separate their labs 100 billion miles apart. Doesn't matter, according to the theory, according to the predictions of the theory. And Alice, Bob, and Charlie are making spin measurements, so they're using these, we always show by these Stern-Gerlach magnets, which create an inhomogeneous magnetic field, little pointy part we can think of as the up direction. And the deal with these magnets is that you can orient them in space in any direction you like. And part of the maybe surprising predictions of quantum mechanics is that when you do that and you send one of these particles through here, it will either be deflected a certain amount up, that is toward the pointy part, like this would be an up result, or the same amount away from the pointy part, that would be a down result, right? And you can set that in any direction you like. Here, this is a down result. Here, this is an up result. We only care for the purposes of this argument that Alice, Bob, and Charlie have the option of sitting it either in the X direction or the Z direction, okay? Where here the X direction is horizontal and the Z direction is vertical. So this would be a situation where these 2 labs are set in the Z direction and this one's set in the X direction. Yeah. And whenever you do this, you'll either get up or down. Good. Now we've got a pair of predictions of quantum theory for this particular GHZ state, and they're very simple to understand. Now, we can imagine that Alice, Bob, and Charlie are flipping coins or doing whatever the heck they want to decide randomly on any given run whether they're going to set it this way or that way, right? And so you would think, well, if they're really doing it randomly with 50% probability, there are 8 possible global configurations, and each one will come up about 1/8 of the time. We only care about the predictions for 4 of those cases, right? The other 4, we just don't, I mean, it makes predictions. Quantum theory makes predictions. We don't care about them. Just delete that data. It doesn't matter. Look at just all of the results for these 4 configurations. If they all happen to choose the X direction, right? So if they're all horizontal, then with certainty, the theory doesn't tell you exactly how many up and down outcomes you'll get among the 3 of them, but it does say it'll certainly be odd. Right, 100% of the time, always, always, always odd. Sometimes 1, sometimes 3. Okay, that's the other nice thing about this example is all the math you have to know is even and odd. Right, if you understand even and odd, you're golden here. If on the other hand, 2 of the detectors are set in the Z direction and 1 is set in the X direction, which can obviously happen in any of 3 different distinct physical ways, then again, you get a 100% surefire prediction that you'll get an even number of up outcomes. Could be 0, could be 2, but you'll never get 1 or 3. Those are the predictions. That's it. What do we conclude from this? Well, the nice thing about these surefire predictions, you'll notice, if I know that there have to be an odd, in a certain circumstance, I say, they all set to X. So there's certainly an odd number of up outcomes. Then if I happen to know any pair of them, I know what the other one has to be, right? There's a certain inference from Alice's result and Bob's result to what Charlie's result had to be. This is like the EPR correlations that Einstein, Podolsky, and Rosen used in their original 1935 paper that involve perfect correlations, right? The nice thing about perfect correlations is what? The nice thing about perfect correlations is in a local theory, it rules out indeterminism. Right? It tells you if you've got local physics and these 2 experiments are happening far apart, let's say at space-like separation, then the results in each of the labs has to be predetermined. Why? Because, I mean, let's just take the simple case we're familiar with. In the Singlet state, if they both measure spin in the same direction, you'll always get one up and the other down. Sometimes you'll get it this way, and half the time you'll get it this way, and half the time you'll get it this way, but they'll always be oppositely oriented. So if I know one, I know what the other is. And if anything really fundamentally probabilistic or chancy happened on this side, the question is, how in the world does the other side know what to do? Right? I mean, Bell puts this very nicely in Bertelmann's Socks and the Nature of Reality, if you want to read. But that it's a very simple argument, right? There's no problem getting a result like half the time you get this and half the time you get that. Okay. In a deterministic theory, it's trivial, right? You just predetermine the results, and half the time you predetermine them this way, and half the time you predetermine them that way, and you never predetermine like this or like this. And so there's nothing in that phenomenology that suggests non-locality. That was the EPR point. But man, if there was something really, really fundamentally chancy going on, if God were playing dice, you'd be in trouble. That's why, and I'll just say this, Einstein wasn't worried about the indeterminism of quantum mechanics. And he says that, it's said in letters. He's worried about the non-locality. And there's a beautiful thing. He says that God plays dice and uses telepathic methods, as is proposed by the current understanding of quantum mechanics. It's the telepathic methods bit that he doesn't like, right? The non-locality. Okay, so first conclusion is because we've got these perfect odd, even things going on, if you want to recover this data in a local theory, it has to be a deterministic theory. You have to predetermine at the source exactly what each of the particles will do under each of the two possible experimental settings they might run into, because they don't know what they're going to run into. Depends on how Alice and Bob's coins come out or whatever. Good. So nothing can happen by chance. That's our first conclusion. It has to be predetermined. Now we have this is again due to Merman. It's really beautiful, nice little graph here. We've got this circle represents if in lab 1, Alice's lab, her thing is set in the X direction. This represents if her thing is set in the Z direction, okay? So these are, the circles represent experimental situations. X, the 1 lab set to X, the 2 lab set to X, the 3 lab set to X. And you'll notice that in this diagram, these 4 lines correspond to the 4 global experimental situations we care about. The dotted one is the one where they're all set to X, and the other 3 solid lines are the 3 possible situations where 2 are set to Z and the other one's set to X. Okay? So now we ask a very clear question. We just proved that in a locally causal theory, we have to predetermine for each of, we have to write U or D in each of these circles, okay? Predetermine the outcomes. And we want to predetermine them so that we'll get the right result no matter which of those 4 experimental situations happens to show up. All right, let's try. So we know we need an odd number of U's along the dotted row. There are obviously many ways to do this. Let's try this. Let's just make those all U's. So I'll stick 3 U's in there. So if they happen to all check in the X direction, I'm okay. Let me just kind of randomly stick in a D here in the middle just because I'm tired of U. And now let me try and finish it out. Remember, I need an even number of U's along the solid lines. So U, D, I'm forced to a U here. And now I'm screwed, right? Because I need a U to make this even, and I can't put a U to make that. And you might say, well, maybe you just made a bad guess somewhere, but there's this lovely argument that Merman gives. He says, look, you think you can do that? This is just a mathematical question. Can you put U's and D's in this graph that satisfy simultaneously all 4 constraints? If you think you can, imagine I've got little tokens with U or D written on them. Okay, pick up those 3 and throw them in a hat. I now have an odd number of U's in the hat. Pick up these 3 and throw them in a hat. Even. These 3, even. These 3, even. Okay, so I threw in odd, even, even, even. I now have an odd number of U's in the hat, but I picked up every token twice because every single of these lies at the intersection of exactly 2 lines. There's ain't no way I'm going to have an odd number of U's in the hat. Period, end of story. That's a mathematical proof. No locally causal theory can produce this kind of data. But as a matter of fact, the world does. For anybody interested, this is the relevant GHZ state written out in the X basis. And you can notice I only have terms where there's an odd number of X ups. I have all 4 terms. They're equally likely because I have halves here. These negative signs are really important. If you want to know what happens in the other circumstances, just rewrite it in the relevant basis, say the ZZX basis, and you'll see that you'll get evens. Okay, how can that happen? Well, I want to talk about how it actually does happen according to a particular theory, real theory that specifies how the world works, namely Bohmian mechanics. But I'm going to take a simpler case. I'm going to go back to the singlet state. You'll remember the singlet state is an entangled state of a pair of particles such that if I check for the spins in the same direction, any direction I like, but in the same direction, I'll always get opposite results, one up and one down. Okay. If you have an actual theory, you can go into the guts of the thing and say, all right, physically, what happens according to this theory? What's the causal structure? And just the fact that I always get opposite results, that could be explained locally. But it turns out in this theory, it isn't. Even though you don't need it in this theory, even just to get this simple singlet state behavior for always measuring in the same direction. In fact, it's a non-local theory. It has non-local causation. So I just want to explain that. What's Bohmian mechanics? Okay, so this thing, or sometimes called the pilot wave theory, sometimes it's called the Bohm theory. I say you have to give me an ontology and a dynamics. The ontology is there's a quantum state, which is represented by a wave function. Everything you might ever call quantum theory has that. And in the ontology of this theory, it is particles. Just plain old regular particles, little tiny objects. Okay, they might be point-like. You want to make them a little fat, go ahead, I don't care. They're well located and they follow continuous paths through space-time. Okay, that's the ontology. Chairs and tables and cats and people are made out of particles in certain chair and table and cat shaped configurations, and they move around because the particles move around in just the way Democritus would have told us. You explain the macroscopic world by reference to the way the microscopic constituents are behaving. So that's the ontology. What's the dynamics? Well, for the quantum state, it's just the usual Schrodinger evolution, that guy that every quantum theory uses at least some of the time, where this is the Hamiltonian operator. I take it everybody, and we have a time derivative that's telling us this is dynamics, how things behave in time. That's a linear equation, blah, blah, blah. Okay. What about the particles? Well, the particles also are governed by a very simple equation. It's called the guidance equation. This is a nice way to write it. You'll notice that psi shows up in the guidance equation. It means that where the particles go depends on what the wave function is. Okay, that's the sense in which the wave function is piloting or guiding the particles, because their dynamics is a function, whereas you don't have any, back here, there's no mention of the particles, right? Okay, so that's the guidance equation. This is how the position of the kth particle is changing with time. And you just take a kind of kth gradient here. You might wonder why I've put a psi star on the top and bottom here. That's to deal with spin. Won't go into take the imaginary part of it. But anyway, you see that equation. Good. That's the theory. I just gave you the theory, the non-relativistic theory. Suppose we prepare a state in an eigenstate of x up, but I measured in the z direction. We know the quantum prediction is 50% up, 50% down. Since a deterministic theory, there has to be something that determines whether an individual particle goes up or down. It's not the wave function, because the wave function, I do this many times, and after a while I get about 50% go up and 50% go down. The wave function is always the same. It's got to be the particle position. And that's what it does. It determines where it goes. And in fact, in an extremely simple way, here's my Stern-Gerlach magnet. Here's the central axis of symmetry. If the particle initially starts out above the axis, that guidance equation will deflect it up. And if it starts out below, that guidance equation will deflect it down. Simple. What about the singlet state? And here, if you don't know this, David Albert explains this very nicely in his book, Quantum Mechanics and Experience. What about the singlet state, where we know one of the particles will go up and the other will go down? How is that determined in this theory? Now, you might think, well, I guess if we're the same, it means either they're prepared this way or prepared that way, right? With one up and one down relative to the axis. But no, you can start with them both up. You can start with them both down. That's okay. Good. All right. But what will happen? What happens is the first one to get to its detector does what I just said. If it's in the upper part, it goes up. It's in the lower part, it goes down. And the second one, this is in the non-relativistic theory, so we don't have any problems about time order, is then, and again, you're just following out the guidance equation, goes the opposite way. Okay? And so the causal structure is non-local. That is, where Bob's particle goes can depend on when, not just what, but when Alice makes her measurement. You might be able to say in this theory, oh, Bob's particle went down, but if Alice had just delayed her measurement, it would have gone up. Clear causal connection produced by counterfactual dependence. And so we get in each run, we either get this causal diagram or we get that causal diagram, depending upon whether Alice or Bob's does their experiment before the other with respect to time. Okay, but it's non-local in the sense that the arrow is going across. And therefore, there's nothing in the data that's going to be restricted by Bell or CHSH because you have those arrows. And there's nothing, the causal structure is perfectly clear. You understand what's going on causally. There's no non-classicality. There is non-locality. Now, the last point I want to make, and I'll just make it in one, this is what the whole thing was going to be about. In the causal modeling literature, this kind of structure has a feature that's called, quote, fine-tuning or unfaithfulness or unnaturalness. Okay, it has a feature that formally it has a feature that goes by those names. And that sounds like an objection, right? A reason not to like this theory. Why? Well, if a fine-tuned theory, just generally you think is methodologically suspect, if we think about the word fine-tuned. And unfaithfulness is actually grounds for divorce. So that looks pretty bad. And unnaturalness, my God, we're doing natural philosophy. You better not have an unnatural theory. So you might say, well, that's the argument. The argument is, look, we can analyze this theory and they turn out to be fine-tuned and blah, 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 blah. So these are bad theories, okay? Now, here's the actual example, finely tuned bells, no fine-tuning, faithfulness, okay, all this terminology I just said came up. No classical causal model can explain all this without fine-tuning there. And this was also from this very conference, no faithful classical causal model, blah, blah, blah. No faithful classical causal model, bad, bad, bad. Boom, bad, unfaithful, okay? Fine-tuned, bad, bad, bad. Now, all I want to say, and this is really the end of it, this is a rhetorical trick. I want to discredit quantum field theory. So I introduce a piece of technical terminology and I get to define it because like Humpty Dumpty, I can define my terms. A theory is totally unacceptable by definition, by my stipulation, if it uses an infinite dimensional Hilbert space. Well, by definition, quantum field theory is totally unacceptable. You can't complain there, but we shouldn't take seriously any theory that's totally unacceptable. Now, of course, there was a trick there, which is that I removed the quotation marks, right? I went from the technical meaning that I defined to the everyday meaning, which is pretty bad, but that's just a joke. Nobody take that serious. That's all that's going on here. Why do I say that's going on here? Is this a fine-tuned theory? Look, I gave you the theory. Let me just remind you, this is the theory. You think that's fine-tuned? Show me what's fine-tuned in it. Right? We had an example before where you only get a result if some row is set to a half. And then you might say that's fine-tuned because rho could be any of these values and you only get this result when it's set to a half. There ain't nothing to fine-tune in this thing. So in the normal sense of fine-tuned, it is not fine-tuned. If it comes out being, quote, unfaithful in some sense, too bad. Why should I care? Perfectly acceptable theory. Clear, sharp, comprehensible. And so if your criterion for being fine-tuned says that this theory is fine-tuned, the problem's not with the theory, it's with your criterion. Bad use of terminology. Okay, and I would argue similarly for unfaithful and unnatural, where those things come up. Also, sometimes people complain it's contextual, so what? Okay, so.
Thanks a lot. So, well, we are already over time, but we'll have questions. Yeah, of course.
Thank you. Thanks very much, Tim. I've got a comment and a question. I just wanted to make a quick comment, and that is, when you were referring to the fact that people didn't understand the GHZ, I just wanted to make it clear that it wasn't Miriam, who was the speaker at the time, who didn't understand what GHZ was. She, when you're referring to that talk, because a lot of people jumped in. Yeah. Yeah, but I just wanted to make that clear in case anyone misinterpreted what went on in that exchange during Miriam's talk. Anyway, but my question is, so with Bohmian mechanics, which I don't really know a lot about that interpretation, but my understanding from what you've said is that there's no testable implications of that theory that go beyond quantum mechanics. So anytime
there's no testable implications of quantum mechanics that go beyond that theory, and it has the advantage of actually being a theory. Okay, so that's I do understand that correctly then. So typically in physics, actually, let me just make it clear. It's not clear. Okay, I mean, when you get into fine details, you ask questions which nobody asks. Like, suppose I do an Aronoff-Bohm experiment, but I change the flux in flight. Okay. So I can do arrival time experiments. It's not even clear how you make predictions about that in quantum theory because there's no time operator. So when you say, do they make all the same predictions, that can be a much more subtle question, and you can't even ask it until you actually have a well-defined theory on the table. Yeah. Okay, so I guess to finish off my question, the question was that you're talking, your preference for it is, from what I understand, is the fact that you think, that it gives you an ontology and it gives you a set of dynamical equations, and that's something you would like of physical theory. What about the fact that physical theories also are often preferred because of their usefulness? So physical theories will tend to stand the test of time when people use them and when scientists use them in communication and in solving problems. And to my knowledge, no one uses Bohmian mechanics. No working physicists use Bohmian mechanics to solve problems. So I'm just wondering if that poses any problem. I'll tell you this, working chemists do. Chemists who actually have to deal with much more complicated systems than physicists do. Physicists don't even get up beyond helium, usually, to what they can do. Chemists have to worry a lot about electron orbitals and how electrons behave for large macromolecules. And they actually use Bohmian mechanics. They use those equations when they're doing numerical simulations to figure out how to put fine grids where the action is going to happen that's going to be physically relevant for the way this thing comes out. So yeah, people use it. Furthermore, the entire point, the effectiveness of the quantum formalism as it's usually used, the quantum predictive formalism as it's usually used, is explained by Bohmian mechanics. So of course I can use something that's effective for making predictions, not understand why it works. I don't really care about, I only care about predictions insofar as they give me ways to think that theories are worth taking seriously. Not because I care about predictions per se. Engineers might not care. They just care about the outcomes. They just want their chips to work. Okay, fine. I'm not an engineer. Not even a physicist. I get to be a philosopher. I just want to know how the world is.
So I think there is also a question online, so the online people can ask directly, I guess.
Yeah. I don't know if, did you hear Julia Rubino's talk on experiments, beautiful talk, experiments in which the time order, there was this, in the process of things happening.
It wasn't what she meant. Yes, I heard the talk, but that's.
I was wondering how Bohmian mechanics deal with that.
No, what she said was extremely misleading. She had Alice and Bob, but each of Alice and Bob could make their experiments at 2 different times. So to do this properly, that is to go down, not to the generic level, but the specific level, you needed not an A box and a B box. You needed an A early box, an A late box, a B early box, a B late box. And the superposition was first to Alice and then, so Alice early, Bob late, or Alice or Bob early, Alice late, but that wasn't any indeterminacy about the time order of those four events. So that talk, the way it was presented, was extremely misleading in saying that this had something to do with indeterminate time order. It has nothing to do with indeterminate time order.
Is Bohmian Mechanics good with that duplication of the different Alices and the different Bobs? I mean,
that's just
the talk was pretty clear about that duplication.
Look, any theory can deal with that. Alice is sitting in her lab and something's going to come in at 12 and she can do something to it, or something's going to come in at 12:30 and she can either do the same or something else to that. That's all that was going on, and the same for Bob. There had to be enough time for the actual single particle to get from Alice to Bob, right? I mean, there was literally a physical particle being sent from Alice to Bob. That has to be time-like separated. There's nothing space-like going on in that. It's literally, do I first send it to Alice and then Alice shoots it over to Bob, or do I first send it to Bob and then Bob shoots it over to Alice? And this was, there was nothing about indefinite time order in that setup.
But those two possibilities show interference terms is the issue.
Well, sure, but that's just normal. That's like two-slit interference.
Yeah, but
that's just normal interference stuff. Of course, you get that out of the theory.
So if it's fine, I propose that we pass to the next question of Eric.
Thanks. So yeah, I wanted to ask a question about your definition of local causality. Maybe could you go back to your slide where you defined that?
Sure.
Maybe while you do that, maybe just a comment also on
causes lie in the past of their effects. So all the causal arrows in a relativistic setting, the causal arrows are always between time-like or possibly like related events, right? That's all.
Right. Okay.
But
but it's not all, because the definition of local causality, we can think of that as being the conjunction of relativistic causality plus Reichenbach's principle of common cause, which says that two events are correlated if there is a common cause in the past, there's a common cause, but if you assume relativistic causality must be in the common past like one. But importantly, such that conditioned on the common cause, the correlation is factorized. Or another way of putting that is that a full specification of the causes of an event fully specify the probabilities for that event to occur, or if it is deterministic, it determines which event is going to occur. And you omitted that from the definition. So, but that's an important part.
I didn't. This is the obvious definition. It's the one I'm using. You want to define it some other way, define it some other way. But this is the obvious thing to say.
The important thing is that if you don't include the other thing, you cannot prove Bell's theorem because you can reject.
Of course you can. I just did. I mean, no, I proved for GHC you can't get the GHC predictions out of a locally causal theory.
The hidden assumption. And
no,
I
there's
agree,
no hidden assumption.
The hidden assumption is that the causes of the event fully specify the probabilities for the event to occur. Therefore, if these two things are correlated, then
I made no such assumption.
Determined by their causes.
I made no such assumption. I made no such assumption.
Okay, then I would like to see you prove that formally without. Well, here's a proof that there is a such assumption, because that assumption that he wrote there in the graph is maintained in quantum causal models. That's precisely the point of quantum causal models, is to maintain the idea that the causes of the event are in their past like Horne, but the complete specification of the causes do not fully specify the probabilities of the event in such a way that events which are space-like separated become irrelevant for predictions of other events. So it's the second part, the quantitative part of Reichenbach's principle, which is violated in quantum causal models, but not the thing that you wrote on the board. So there is a constructive proof of reproducing Bell's theorem while maintaining the thing that you have in the board and everything else that you assumed. Therefore, you cannot have proved that.
No, there's not a constructive proof relative to the definition. Look, you can define quantum causes to be whatever you want, okay? And maybe you can prove something.
It will satisfy the notion of local causality that you have on the board.
Let me just say something. In a locally causal theory, if I have fundamentally probabilistic events, and you can have a stochastic locally causal theory, the condition now is that the joint probability for space-like separated probabilistic events is just the product. Okay, so there's no correlation.
No, not by what you wrote.
Yes, look, that's the definition I'm using.
So I'm sorry. I guess that this has to be like written and
again, go
answered in more time. So I propose that we stop here, right? And well, it's the end of the morning session, so good lunch.